First talk by Mr. Sharat Kaul, the consultant Indian representative of INAMI, International Electronics Manufacturing Initiative, and he is going to deliver his talk on the semiconductor manufacturing ecosystem transformation. And I'm extremely happy to introduce Mr. Sharat Kaul, who has been one of the motivating force behind us to be a part of this semiconductor ecosystem, which is emerging with the maximum force in the current scenario. Mr. Sharat Kaul is a senior leader in global semiconductors and advanced electronics manufacturing, with over 30 years of experience spanning Texas Instruments USA, Synapsys, and multiple entrepreneurial and national ecosystem roles. He specializes in building high reliability, strategically resilient manufacturing systems with deep expertise in India's electronics packaging and semiconductor localization strategy. As executive director at Krypton Solutions India, Sharat leads one of India's most advanced ITAR certified surface mountable technology and electronic manufacturing services operations, delivering low volume, high mix PCBA services for global leaders in defense, aerospace, semiconductors, and medical electronics. Krypton supports classified mission critical applications operating at the highest global standards for quality, traceability, and compliance. Previously, as Vice President of Strategy, Innovation and Execution at IESA, he helped shape India's semiconductor policy framework, including early stakeholder engagement for project-linked incentive, design-linked incentive, EMC 2.0, and ASP-ECS. Today, he remains a trusted advisor to government missions and industry on localization, fab readiness, OSAT enablement, and high-performance computing strategy. At INAMI, Sharat drives global growth, strategic partnership, and member value as the India representative, leveraging his deep industry insight and cross-border experience. Sharat holds degrees in electrical engineering from University of Texas at Dallas and business from the Cox School of Business, SMU. He currently advises global semiconductor firms, Indian industrial leaders, and government agencies on advanced manufacturing, strategic partnerships, and India's emerging semiconductor landscape. With this brief introduction, I welcome Dr. Sharat Kaul to deliver his talk. Please, sir.
Thank you, Dr. Bosco, sir. I'm not a doctor yet, so I'm just a mister. So namaste, vanakkam, thank you. It's absolutely an honor for me to be here, and it's a privilege to be able to be associated with an esteemed University of Shastra, with the brilliant faculty and wonderful, beautiful human beings in the leadership with Dr. Vaidya, Vice Chancellor, and Chancellor Swami. So thank you so much, sir, for this opportunity. My dear friends on the call, dialing in from all over the world, thank you so much for joining us today. For my friends in India, good morning. And I hope that we'll be able to go through this journey together and discuss about ecosystem transformation. So this is the abstract that I have submitted to Shastra University for this workshop. And I wanted to make sure that we covered Taiwan as well, because Taiwan, this industry would not be happening without Taiwan. And the abstract was about the journey from the transformation that the industry, the global semiconductor industry, has witnessed and is witnessing and will witness. And just to take us back, the first transistor, 1947, at the global level. Then in India, BEL had the first germanium semiconductor in 62, and then with the Soviet Union, and then the supercomputer from US came in 64 when we were starting semiconductors. And today we have the fastest supercomputer, which is running at 12.8 terabits a second. So this doesn't happen in isolation, and it happens. And now that we're coming into this era of AI, and we're seeing different geopolitical dynamics going on with isolation and your friend or my friend, and all of these lines are being drawn. Even if one piece is missing in your semiconductor, then your semiconductor doesn't ship. And if your semiconductor doesn't ship, then your car doesn't ship, your TV doesn't ship. So we have to be very clear to understand the vulnerabilities that any country has, not only India, in our aspiration to be self-reliant. So the talk is going to be its impact on the Indian semiconductor mission. This is a simple agenda. I'll just briefly talk about INEMI to put things in context. Then, since the talk is about ecosystem transformation, I just thought I would talk about what is the ecosystem for electronics, and then what is transformation in electronics. And then I was asked to talk about advanced packaging. So I have a few slides on chiplets and heterogeneous, and how we came to that point. And then really, we want to walk away from this talk with some actionables. And I'm really pleased to say that there is beautiful work going on in the country. And the brilliant minds of the country have been working tirelessly for us to make this mission a success, mission success. And those brilliant minds, we've consolidated this information, and I'm going to be presenting what the need is and what potential solutions are there, and then how you can help. So INEMI is a 30-year-old industry association body. It's a not-for-profit. Just like the transistor was invented in Bell Labs, INEMI was invented in Bell Labs. Bell Labs invented and said we need to have an industry body where we all cooperate, where we all share our lab resources. We give our resources for projects and roadmaps for the better good of the electronics industry. So today we're nearly 90 members across 20 countries. We have 35 project portfolios. In those, we have around 400 or 500 projects. And those projects feed into the roadmaps. The roadmaps, we project technology readiness for various aspects of electronics and manufacturing for the next 10 years. So every year, for example, today, this is 2025, our teams, the industry teams, generate the roadmaps to 2035. And then those gaps, in order for us to get to high volume production, the project teams, we write the SOWs, the contracts, and the agreements for all of those companies to work together and solve those gaps. And this is the gaps we're talking about. Many of my friends on the call are students, and you're working on innovative ideas, principles, and concepts. You have it on paper. It's an R&D. Really, getting it from your concept to actually reliably, a product that reliably works in semiconductors is a huge pitfall. And this is where INEMI tries to come in and bridge this gap to get us from TRL level 3.5 to 6.5. And we have three basic pillars: smart, sustainable, and system. Smart is on the digitization and the connectivity and the making sense of massive amounts of data, what we call from shop floor to top floor, and concepts like digital twin, lights out manufacturing, robotics, and much more. And then sustainability is a huge initiative where we talk about ESG, environmental safety, recycling, circular economies, net zero carbon emissions. Because just imagine the amount of electronic waste there is. And so we discussed that in details. And by the way, we do roadmaps and projects on these. And then of course, system integration, which means at the fab level, the component level, the package level, and at this complex integrated system level. This is the actual manufacturing value chain and how they all complement one each other, their intersections. And then I don't want to go into detail, but to the left side of that we have open to the industry for the roadmap contributions. And then to the right of the screen is for the projects, which is members only. And INEMI program manages all of this and makes it happen on time. And now we want to bring India as part of these roadmaps. We don't want India to have separate roadmap from the rest of the globe because of the supply chain. And that's why I'm here today. So we have 90 members across the fab, packaging, board assembly, and system integration. I won't go into detail, but fair to say we have academia, we have systems, we have applications, equipment suppliers, et cetera, material suppliers, raw material suppliers, industry bodies, etc. So that's a little bit about INEMI and setting the context. I'm going to talk about ecosystem now. And this is the slide from our board of the directors on INEMI, Ravi Bhatkal from McDermott Alpha. And the way to read this slide is actually from top to bottom. And if you see these slabs, this is what touches us every day in the human environment. Everything that touches us today needs energy. And those energy flows can be broadly classified into these categories. That energy flow between the end apps is managing the data. And the data is given to us by smart devices and sensors. And then at the lowest level, we have the communications and values. So what that means is on the right-hand side, what are those imperatives to localize? What are the must-haves? What are the items that are mission critical for us, for our survival, for buildings, automotive, medical, environmental? And that's each of these flows. Energy flows have semiconductor content, information has semiconductor content, and the vital components, those sensors, the analog to digital converters, the microprocessors, all have to have different requirements in terms of power, performance, and area. Energy flows would be at high voltage DC and low and high currents for EV. Information flow has to be low power. Edge devices has to be very low on power consumption because they run on batteries. We have to have RF, strong RF, so we can send the signals over the airwaves to satellites, to ground stations. So when we talk about the value chain and ecosystem, this is the ecosystem today. And if you see, there's a deliberate intention to have these boxes all separate. One might ask yourself, why don't you have materials cutting across? Why don't you have components? The reason is because all of these individual pillars are all ecosystems in themselves, and each of these boxes within them are also ecosystems. And the industry, now India is planning ahead for the future, we would like to have this value chain integrated and connected so we don't duplicate. And so we leverage the common foundation. Today we have one fab in the country, which is SCL, and we're bringing our second fab online with Tata. And with the strength of our government and the speed of execution, yesterday, Dr. Charan Gurumurthy told us that they're ahead of schedule with their fab. So that's just tremendous news. And we hope to see them generating revenue and wafers. Materials, components, equipment, they have to do tie-ups with companies every step of the way to ensure that there's not even one gas, not even one chemical, not even one piece of component is missing to fabricate the device. Similarly, the enabling activities, this is physical at the top level, and at the bottom are the enabling activities. And we're going to be adding another layer under here, and we're going to be changing manufacturing to process manufacturing. And we're going to be having another category here called smart manufacturing because they're different. But as you can see, once you start filling in the logos for India, it'll all be empty, the ecosystem. This top part, if you were to ask myself at the global level to fill it, then it'll look like that chart of all the logos, where we would be able to fill in, say, McDermott Alpha does materials and fab, packaging, board. IBM does board, final assembly, and circularity. Applied Material does fab, packaging, board. I hope you understand the point I'm trying to get. We can actually fill in company names at a global level. And that's how semiconductors are operating today, how semiconductors have been operating across the globe. And there's critical capabilities, and there's many, many vulnerabilities in this for India. And for us to draw this map and fill up the logos of Indian companies is exactly what we are trying to do. And we've added a fifth component here on the right called circularity, which is critical. What is circularity? Circularity means that the device is finally assembled and put in our phones, and we're manufacturing millions and millions of iPhones and laptops and servers, and then we throw away a mobile phone, or we get a new one. Maybe we refresh after 3 to 4 years, and then we may give that phone to someone who is in need, and then they will change their phone in 3 to 4 years because it gets outdated. And then what happens to that hardware? And are we thinking about that hardware over here at the left? So circularity literally means that we have to come back to where we started and think about the start in mind when we're designing, modeling, manufacturing, testing at the fabrication level. INEMI and our mission in India is to enable this ecosystem, and we're going to be doing roadshows across the country. And so we'll talk more about that. So this is the ecosystem today. So if we were to put all of these logos, we can put them in these boxes. And as you can see here, these are the equipment guys on the left. We have, I wanted to talk about Taiwan here for a moment and the importance of Taiwan. There was a gentleman by the name of Dr. Morris Chang, who was a senior vice president at Texas Instruments. And when the first semiconductor devices were built back in the early 70s by the first integrated circuit by Jack Kilby from Texas Instruments, and then when we started to get the process of design, fabrication, we literally were doing them on paper, and the layouts and on the basic computers. And all that existed in the world was companies that did everything from concept, design, fabrication, packaging, board, and product. So Texas Instruments was one of these companies, which was called an integrated device manufacturer, or IDM. Then we had, in USA, we had Intel and IBM even at that time. But then a transformation took place which would have global implications that touch us today, and has become a critical pivoting point in the most valuable companies in the world. And that's the concept of foundry. And basically what Dr. Morris Chang said was, Texas Instruments were making products and we're able to manufacture these, and we see, and then we're going to talk about scaling and Moore's law. And as you progress towards Moore's law, he knew that the future would be that in order for the fabrication and manufacturing to be successful, we have to open it up. We have to allow more design to come into the factories instead of only our designs in our factories. We need to be able to set up a foundry where people can give us their input files, and we have a sign-off process and a quality check, and we just load up our fabs, and that's how we can transform the ecosystem and get more innovation. And that was a pivotal point. And did you know today that the top 3 companies valuation, NVIDIA, I think you would have heard of, I think you would have heard of Broadcom, Microsoft, and Apple, they don't fabricate chips. They send all of their chips to TSMC because they send it to the foundry because it's de-risking. And TSMC does foundry the best in the world. Once this pivotal point took place and Taiwan became the foundry for the globe, we saw a mushrooming of fabless semiconductor companies now. Fabless literally means I don't have a fab. They're IP companies, intellectual property, in the era of chip design from RTL to GDS2. And they all have multiple billion-dollar valuations. And more IP comes to the market. And now we're seeing IP cores. You would have heard of PCI Express. You would have heard of USB. You would have heard of HDMI. Newer standards are coming up. I'm going to be talking about UCI in the context of packaging. And what also happened, just like you had foundries for fabs, there became foundries for packaging. And those are called OSATs, outsourced assembly and test. Now, India has 4 to 5 OSATs now. So you can see we have 2 fabs, about 5, 6 OSATs. We have many SMTs in India. we need to build that ecosystem and value chain for equipment, raw materials, testing, assembly, this left-hand side. And almost all of these global companies are motivated to set up in India. And most of these are INEMI customer members, I would say. So I've talked a little bit about an ecosystem. I hope you have a clear idea of, we're talking about something of global proportions and about geopolitics and about self-reliance and the different areas and segments which we're working within electronics. Now I want to talk a little bit about transformation, and it started in 1958 by Robert Noyce when he decided to put a piece of silicon or germanium, I think it was silicon, across two terminals. And the unique thing about this was he put a third device, which was another electrical device, which was a gate. So what he was able to do is, instead of having a manual switch like we have on the walls, he was able to make an electronic switch that could be controlled. And that was the genesis of a transistor, the integrated circuit. On, off, and a gate, an automated switch. This gate is what's transforming the globe today. And then if you fast forward, and then once this happened, we immediately started learning how to productize it. And the earliest germanium and the first supercomputer, the so-called supercomputer, was the Cray, by Cray computers, which was the CDC 6064. And from germanium, at the advent of silicon, they moved to silicon. Germanium, silicon, these are all carbon-based with valency 4. So depending on the doping and depending on the application, germanium, silicon, and etc. have different pros and cons. But we won't go into that today. And basically what I want you to take away is 1964 and 3 megaflops. This 3 megaflops, mega 10 to the power 6, is, and flops, operations per section. I think this is fixed point operations per section, check. And then what I'm trying to, a takeaway is, this was the advent of a supercomputer for the first time, 3 megaflops. And you're seeing 9 million USD in 1964. Now we talk about Moore's law, and he'll be hearing this over and over again, and you need to remember it like Newton's laws of physics. And it's holding true today. And you know, throughout my career, I started my career in 1993, I would say. And in Texas Instruments, I was a product engineer on the test floor, and I was working on 0.35 micron, right over here in 1996 and 97. So this dramatic shift from 3 micron to 0.35, I was right in the middle of that when Moore's law started ticking like a clock. And every time it just, our gate width would be, if we go back to this basic diagram, this gate width was 0.35 microns, and it just kept on going in half, 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 half. That's Moore's law. And when that distance between the N wells decreases and decreases, the current decreases, the breakdown decreases. So that means you can't put too much stress on the gate. So as all of these things get as this shrinks, everything shrinks, the area shrinks, the power shrinks, and not only that, naturally, as you know with physics, the distance from here to here shrinks, which means the speed increases. This is what Moore's law has transformed this industry and is transforming it today. And if we can keep pushing the laws of physics, and if in Moore's law, I would also like to indicate that we were going planar, which means I mentioned in one unidirectional gate width. As we progress past 10 nanometers, we start getting into physical effects which limited us from going planar, and we had to go vertically up now. So now you're going to see three-dimensional structures. Actually, three-dimensional structures came earlier with FinFET. But what we're seeing is remarkable inventions and innovation in order to us to cross the borders of physics. And today, I shouldn't say today, but the golden race by TSMC, Intel, and Samsung is who can be the technology node leader. And how do those technology nodes get validated, verified, tested across temperature, and work in space applications? And let me tell you, 3, 5, 7, 10 probably aren't in automobiles, or I shouldn't say that, but you really have to validate those technology nodes and make sure they're robust. So typically, when mission critical, you try to have a safe node. But today, Intel is trying to announce 1.6 angstroms, which is 16 angstroms, which is 0.16 nanometer, 1.6 nanometers, and TSMC is at 2. And we're talking about the gate length of 1 or 2 atoms. And that's the way that this industry stretches the laws of physics and is the most complex, most difficult, and most challenging industry on the planet, and most interesting in my heart. And for Dr. Bosco and all of our members on our staff here, we're all passionate about this. But look at where we are today. From here in 1958 to here, this is last year. We're even further here. We have 3 nanometer silicon, and there's billions of transistors. 220 billion are on the NVIDIA chip, the Blackwell chip that they have. And you can see they have thousands and thousands of multi-cores. They have and I'll talk about the architecture coming up in a moment of what is all of this? Why does it look like this? Why are these shiny? Why are these not shiny? I'll talk a little bit about that. But first, I talked about 10 to the power 6 in the context of megaflops, but now we go to petascale. And India is at petascale. Europe is at petascale. And the globe is marching, as you're witnessing with NVIDIA and the advent of ChatGPT and generative AI, that we're moving to exascale. What is exascale? A supercomputer that can operate at 10 to the power 18 FP, floating point, flops. Okay, floating point operations per second, flops. So from 10 to the power 6 to 10 to the power 18 in 2020. There's only one supercomputer in the globe in a single location that's able to operate at 10 to the power 16, and that's the Frontier in the United States. Europe has reached exascale, but it's distributed exascale, and their system is called Jupiter, and they launched it 2 years back. And then India is at petascale, and we are rapidly marching towards exascale in a distributed fashion. All 3 of these have to make critical decision points on many factors which affect the supply chain and will affect the geometries, the technology nodes, the economics, the reliability that drives. And once you drive the technology on the supercomputer, you have hit the superset of all other electronics, and then you are able to work towards space, automotive, healthcare, industrial, motors, drones, cameras, etc. So this is, for example, the global benchmark. And our global benchmark in India is our supercomputer, which I'm going to talk about. I talked about the architecture, and all of these supercomputers have to decide on these basic 4 quadrants. The GP CPU, which is a general purpose central processing unit, which you all are very familiar about. Intel Inside, AMD, Celeron. These are all x86 architectures, which are complex instruction sets, and they have multiple instruction set lengths, and they have a guide. It's a 1,000-page guide which helps you program these chips and to perform. And out of the, I think it has 800 operations. I think 90% of the operations, you use only about 100 of them. So if you can memorize maybe 100 instruction sets, you can start making an operating creating an operating system and building compilers, and then creating applications like Windows. And the market has been dominated by CISC when Microsoft and Intel partnered. And then came along reduced instruction set, and reduced instruction set where the instruction sets are fixed. And when the transformation took place of design and foundry, and IP companies became emerging, one of the most important IP companies on the globe emerged, which was ARM. And ARM was started out of Cambridge, UK, and that was the first soft core microprocessor. These are the microprocessors. You have microcontrollers and microprocessors, a control logic and a processing logic, which does the math. Okay, so now you're looking at the advent of a reduced instruction set, a design that you can design on your computer and then give it to TSMC and fabricate. This opened up an entire world of IoT now, because Raspberry Pi are IoT applications. And not only that, ARM was very conscious about low power for handheld devices. So if you see Snapdragon, if you see Samsung, if you see the handheld applications which require low power, then it'll be ARM. And then if you see the larger motherboards, then for desktop servers, for supercomputers, and for laptops, you see x86 CISC. What ended up happening then, you have the major the tectonic shifts, as I call them, the advent of the semiconductor, the advent of the supercomputer, the advent of CISC, the advent of ARM and IP and Foundry. Another inflection point was separating the processor elements from microprocessor and microcontroller as a separate, focused, dedicated unit for graphics. Because at the end of the day, you have highly efficient superscalar architectures, which means you can do them in very few cycles, clock cycles, which makes them super efficient in terms of battery power and actually designing the chip. And the school of thought was from Jensen Huang was that, man, these x86s and the ARM cores, I just can't get the physics and I can't get the pictures to come out like real life as I want them to. I'll continue to use x86, I'll continue to use RISC, but when it comes to those graphics, I want to use a DSP and I want to break it out into parallel. So he was the one who started creating he actually can be credited for generating the name GPU, actually, graphics processing unit. And those are superscalar math multipliers that are, when I say superscalar, they're in massive parallelization with the intelligence to branch out those massive calculations in a very efficient, perfect parallelization so that you minimize the number of net cycles, which makes it super, super fast so that we don't wait to see those beautiful graphics on those beautiful games. And if you've seen the transformation, and Jensen Huang and NVIDIA were so successful with gaming that they would actually put their card next on the Intel motherboard card, if you remember, in the old days. And everyone would want to have an NVIDIA graphics card because you want to do gaming. And then NVIDIA said, hey, this PCI card, it so happens that most of AI is processing text is one aspect, but then analyzing pictures from cameras, analyzing videos, and then security cameras, car cameras, drone cameras. He said, oh my God, if I'm using the graphics on GPU, then why can't I use it for AI? And that took NVIDIA stock to the most valuable company on the planet today. And their valuation is $3 trillion. Their valuation will soon, I hope it doesn't cross India's GDP. But that being said, the GPU is a heavy lifter. And that means it's massive superscalar parallel processing and it runs on a highly sophisticated operating system and compiler called CUDA. And that's how they've been able to generate an ecosystem, and they're spreading their tentacles into many other aspects of the data flow, if you were to look at the data flow. And one critical aspect that is, which will continue to emerge, is more and more of the fabless semiconductors to create IP, which would be for a specific application, for a very specific IP, when I say AI application. So there, you're seeing newer, and AI is emerging so fast. And there are studies that show, and in fact, India is also working on studies to see that NVIDIA, for a particular algorithm of AI, whether it's gate checking for attendance or whether it's ADAS, that perhaps NVIDIA may not be as efficient, and there's a lot of room on the table if you by tweaking the architecture to get 50, 40, 50, 60% improvement in performance. Now, just imagine if you're able to get even 10% performance improvement from NVIDIA, and I'll talk about that, and just hold that thought if you're able to get 10 to 15. So now let's fast forward to the frontier. It uses AMD, and now it uses 9,500 CPUs, and it uses their own 38,000 GPUs, which has 8.3 million cores. Okay, and it's operating, as I mentioned, 12.8 terabits per second. And now, when you're operating 8.3 million GPUs, I want to make sure I'm doing okay on time. I have 10 minutes left, sir. I hope I'm okay. I'll try to speed it up. Yeah, I'll speed it up because I need to get to packaging. And anyways, I'll speed it up. But this, it has to be liquid cooled because there's so much. It consumes 13 megawatts. And the data servers that we're planning now in the advent of AI, we're estimating it's going to be 100 gigawatts because of the number of GPUs. And Europe's supercomputer used Intel, and India's supercomputer is using Intel. And now Europe is moving to, they're looking at RISC-V, just like India is looking at RISC-V, which is open source. And they have the Grace GPU 200 and ARM, they're using ARM. India's first generation Param, we used NVIDIA for GPU, and we had, I think it's Intel CPUs, and it was operating at 5 teraflops. And then we were building our own core instead of ARM in Hyderabad. We are creating a 5 nanometer 96 core by CDAC, and it'll offer 4.6. That's just the chip. So then you multiply. This will be the CPU. India is creating its own CPU, and we're partnering with Japan from the Fugaku supercomputer. And today in CDAC in India, we have the Rudra processor, and it's using AMD with 96 cores, and we're putting them across in a distributed fashion so that we'll be having a cloud server for AI workloads. And we're in our aspiration to get to exascale. And the vision in the next 2 to 3 years is a 100 gigawatt server, and they'll have about 85,000 of these HPC chips. And work is going on by CDAC and some private players to build their own HPC chips instead of depending on importing GPUs or importing Intel chips or AMD chips, or even using AMD or Intel chips that are manufactured in India, which they are not. And it's doubtful it'll happen in the next decade. And then I did some back of the envelope calculations about how much it would cost. The NVIDIA chip sells around $40,000 for those GPUs. Everyone's trying to get their hands on the GPU. One of the biggest bottlenecks is the communication from an NVIDIA chip to another NVIDIA chip, or an Intel chip to another Intel chip, or another card to another card. And we need to come up with a backplane, a traffic management system more robust than PCI Express Gen 5, Gen 6, Gen 7. And they're looking for chip to chip at a protocol called UCI, which is Intel UCIe, Universal Bus for chip to chip that Intel is leading and that we're looking at. And that's going to be calling now when we need. So right now we're at silicon for computing. Then there's silicon photonics computing, and we need to get to photonics, which is optical from chip to chip for data server workloads. And then you start reaching, we're very far away from quantum speeds, but silicon will need to fulfill the needs until quantum is affordable and it's reliable. So HPC for science, weather, healthcare, energy, you can Google it. The weather physics requires supercomputers. Genomics requires supercomputers. DNA sequencing requires supercomputers. Otherwise, our medical reports will take weeks and weeks and weeks. They used to take months and months and months. Homicides, now we can do the DNA sequencing, I hope, in 3 to 4 days when it's required instead of months and months and months. So it's transformational. So I'll quickly talk about advanced packaging. I don't, and we have had some beautiful conversations on over the yesterday. So I'll try to take some key highlights. But what you're seeing is heterogeneous systems. What does heterogeneous mean? Heterogeneous means mixed, and that mixed means we have high power devices for energy, as I talked about in the ecosystem slide. For EV, for example, in order to charge a bus, which has a huge battery, it requires thousands and thousands of volts, thousands of amps. If you want to do it in a reasonable time, like 5 minutes instead of 6 hours, how can a bus going from here to Mysore take 6 hours to charge? I mean, you stop, have lunch, and you should come back and go. It should charge within 10 minutes. So that's not a trivial problem statement. Those chargers need to be miniature. They cannot be humongous like the size of a DG. Mobile phones will operate at microamps, femtoamps. They operate at super high speeds and frequencies, whereas probably the power systems operated low. But now you need to imagine from the 1960s, 70s, and 80s and Moore's Law, the motherboards that we're seeing from the old days when we would have desktop computers with the cards, the laptops that we have in front of us, the mobiles we have, they all have their motherboards. Just imagine those motherboards becoming the size of your pinky nail. This is the kind of a good analogy for talking about a chiplet. Those motherboards of the old days, which are, maybe 1 foot by 1 foot, or 2 feet by 2 feet, or 3 feet by 3 feet, or even 4 inches by 4 inches, becoming smaller than the size of your pinky nail. That means that the power supply chip, the power regulator chip, the analog to digital chip, maybe if it's wireless, the RF chip, the GPS, the PCI, microcontroller, the memory, is getting miniaturized the size of our pinky nail. And this is kind of a representation of all of it coming on a common substrate and through vias. And we're miniaturizing, which reduces the power, it reduces the area, it increases the performance, and that's why this is what Moore's law has allowed us to do. So not only that, we're also miniaturizing for power, for those data centers we're talking about. So miniaturization in the context of chiplets is becoming extremely critical because of area limitations, because of the economics, and because of the performance that they offer. And this is a beautiful slide by McDermott Alpha, which just gives you a cross-section of maybe a typical chip. You can divide this complex diagram into three broad categories that McDermott Alpha, which is an ecosystem supplier from chip to box, actually. They do semiconductor solutions, assembly solutions, and circuitry solutions. And within circuitry, you can just see all of these red dots and the different types of chemicals, compounds, molds, coating, plating, metallization, finishes. They all require processing, machinery, equipment, and they all react differently to temperature. The different layers have different properties, so they warp. They become bimetallic strips. If this green, and typically you have to do it on an insulation. And another aspect that we look at in manufacturing in the ecosystem is now when you throw this away, what are the heavy metals that are hazardous to our planet? And now we're looking at substrates which not only are organic, but they're eco-friendly and they provide excellent insulation. We're also finding as we go to higher and higher voltages that solder no longer works, and we have to look at silver, at tin, at other advanced compounds, molds, and materials. As we start getting into thousands of amps, when these start getting fatigued and break and become brittle, when they should be lasting for decades. So this is a beautiful diagram which gives you an idea of a chiplet and how they're stacked upon one each other, the technologies, the concepts like through silicon via, copper to copper bonding, and the effects that current and temperature have at each and every one of these junctions. It's literally like building a skyscraper. We're going vertically, we're going horizontally, and we're going in every direction. So I talked about advanced packaging, and I'll quickly wrap up with the need. So when you run a fab, I agree, we are moving towards robotics. And if you run a packaging line, I agree, it can be run by robotics, but we must have the human in the loop, and we must be having forever. And we must be having the humans to operate those robots and program those robots and make them, give them the data they need to become smarter and be more efficient for us. And who's going to provide that? Technicians and operators like Shastra is doing for Tata and the OSAT. It's a very difficult problem statement to find motivated engineers that would have be interested in a career in semiconductors, who are aware of semiconductors. Once they're aware of semiconductors, we cannot afford to put them on multi-million-dollar equipment, and not only just for their failure, which is okay, but for the product failure and the customer success. When uh, uh, very important products for our globe, electronic products, are on the line. The globe is looking to India because we have the lowest age workforce on the planet, and we have maximum number of engineering colleges, and we are very good with software and math. And it's just by nature that we will be able to be the talents hub for the semiconductor industry, not only design, but also for manufacturing. So if we look at manufacturing for large scale and even exporting that manufacturing for the globe, it's a pyramid. And literally, the bottom of the pyramid, 90% are actually diploma and ITI and BTech, and they have to be trained within 6 months to 8 months. And what Sastra is doing, and what we are all trying to do together with academia and the industry, is come up with hands-on experimentation so they can actually take chips and package it, dice it, mold it. We are also now beginning to have tiny fabs where we're actually doing lithography, and where we need to be today is skilling our youth on advanced packaging and understanding what advanced packaging and the opportunities in advanced packaging for innovation. Now, at the top of the pyramid is where we start getting our more experienced laterals, you can say. And this is the career path that we could aspire to. And these are MTechs. And at the top, of course, is our research and the innovation and the PhDs and the innovations across the ecosystem, whether it be fab, packaging, assembly, or circularity. But you can see the takeaway here is 90% of the workforce needs, which is estimated to be about 1 lakh people by 2030, is 80% to 90% workforce for manufacturing. The numbers are debatable, but the report said that by 2027, 85,000 are required, of which 20% of those is manufacturing. So around 1,700 people in manufacturing, of which divided 50-50, 800, approximately 850 or 900 for fab and 900 by, so you could say 1,000 for fab and 1,000 for packaging by 2027, and that growing to probably 1,500 to 2,000 each by 2030. And then on top of that, you add the export of the talent to the United States and Europe, where all these fabs and even Southeast Asia. So probably, you're looking at about 10,000 people specifically in the area of packaging and fab that we need to skill in the next 5 years. And Taiwan is a critical partner because they are the global leaders in this. And Shastra is doing the best job we can see in this area as well, and with their investments and with their vision. So what is needed? We talked about the gaps in the ecosystem already. I won't go into that. Design, modeling, manufacturing, and reliability. The enablements. We talked about the full chain and investments. So what needs to happen? It needs to happen at the university level through industry university partnerships, through CSR, and funding equipment where we can keep on cycling students with hands-on training through 2 weeks, 3 weeks, 4 weeks, 6 months, intensive courses, so that when they come out, they're ready to go to Tata, to all of these OSATs, to the fabs, and start being productive immediately without risk. We must also continue to bridge the gap between the TRL level 3.5 and 6.5. And how do you do that? With these labs. And we have to share the labs, and we have to be aware of the labs, and we have to understand what the lab capabilities are for specific technology focus areas, whether it's high temperature, high power, or low temperature, low power, whether it's wired or wireless, whether it's in the air, on the ground, or in the water, or in space. And they have to be very, very focused, and we have to understand customers' needs and problems and have that maturity, not to just invent for the sake of inventing, but to understand the customer's needs. And if we do that with our workforce, we will be unstoppable. The industry can participate. Most of the universities are CSR enabled, which means they're not for profits, which means industry also has a mandate that if they're profitable, they have to give 2% of their net profits for CSR, otherwise they get penalized. So the industry is motivated, the universities are motivated, they're qualified, and the skilling is absolutely within the charter of the CSR Companies Act. We also expect the university we expect to train the trainers. So the industry comes in and we do these types of workshops. We come on site and we sit with the university staff. We provide the content, we provide the course curriculum, we work with AICT, and together we train staff. So because if you're able to train the staff, then the trainer can train another 100 students, and then you're able to have a multiplicative effect to reach that 10,000 number. And we need to dedicate time, volunteer time. This is volunteer time we're doing. And we should be on multiple advisory boards and participate like we're doing here, and spread the word, record these sessions and spread the word as much as we can, and use technology. In-kind contributions, which is actual equipment. McDermott Alpha has an SMT line they've donated at Madras. They have cycled 500 students through that line in about a year, and 500 out of 500 have gotten jobs, which are 4x what their father or mother are making at their village. And they're transforming the lives. And we believe this ecosystem is sustainable, and it's a model that is working for India, and it needs to grow, and it needs to grow faster. And INEMI is here to help enable that. And then of course consortium, which is what we're talking about here, industry consortiums, where INEMI can come and help build project teams to work with academia and students. So thank you very much for your time today. I hope this was informative and useful, and you learned something new today. Probably much of it may have been repetitive because of the rich experience you had yesterday. This is my QR code that you could scan if you would like to connect with me on LinkedIn. You could please reach out to Dr. Bosco sir and the team here. I would like to specifically thank the members and the eminent faculty from Lunghwa University of Science and Technology. We are privileged and honored for you to be here with us in India, to guide us in India, to help us be a part of the semiconductor ecosystem. Taiwan has a choice who their friends are, and we're very, very grateful that you've chosen Shastra and such a beautiful institution. You've chosen the correct institution. So we're honored to be working with you, and you have our full support from the industry. And of course, none of this is possible without the Ministry of Education and also our mothership, the Ministry of IT and Electronics. So thank you very much. I'll hand it over back to you, Dr. Bosco, sir, if we have time for questions.
Yes, sir. Thank you. Thank you very much for your wonderful talk, highlighting the current ecosystem and what kind of transformation the whole country requires and what we want to be. So which has been very, made very clear. Thank you very much. And just one question, sir, like as we go forward, how this photonics is going to be integrated with this well-established, integrated circuit technology, and what kind of difference it is going to make.
Thank you, Dr. Bosco, sir. Photonics and optical fiber is not new. Photonics and optical fiber is not a choice, it's mandatory, and it's inevitable. So these are a few foundation. Optical fiber today, as we all know, is drawn under the ocean, and we're able to connect countries. And optical fiber analogy is as you have an eyedropper, and then you can have a fire hose. The eyedropper is Ethernet and today's Wi-Fi, and the fiber optics is like a fire hose. So if we put those in statistics, what your question is how do we provide that hose between chip to chip.
Yeah.
This is what Professor Bosco's question is, and this is an area called co-packaged optics. And how do you provide optical connectivity to the tune of 5 to 12 terabits per second between chip to chip, when today we are around 250 gigabits per second chip to chip? So you're looking at a 10x or 100x, I have to tell you, 12 terabits. Terabits is 10 to the power 12, sir, or 16? I have to check.
10 tera, yeah.
Tera. And this involves technologies and materials in the area of lasers, optics, and sensors and waveguides, directing the lasers in exactly the precise location and carrying that data along these waveguides. India started its photonics journey, what I have read, in IIT Delhi, which started the first photonics lab. And now we have advanced photonics labs at IISc, IIT Madras, IIT Bombay, and IIT Hyderabad. And I'm in touch with Professor Imani in IIT Hyderabad, and we're working on industry consortiums with each of those IITs. And if we would like to set up a photonics focus, then I would help you find a photonics anchor partner. There's many challenges, and I can share a lot of papers and research which is going on in this area. But the bottleneck is making it from the lab POC into a product that can be used in a data center, for example. And I would estimate that we're at TRL level 3.5, and I did some research, and only TSMC is providing silicon grade photonics in the globe today. And there's also indium phosphide, which is another option for photonics, which Hyderabad is focusing on, and silicon and Bombay. And by far the leaders in photonics in terms of potential commercialization and success is NVIDIA, AMD, Broadcom, probably Intel, and they are all working with TSMC. So if Taiwan would allow us to do a shuttle with that photonics wafer along with those big boys, then it would be a very big thing we can do, and start taking the silicon that the rest of the globe is using on our bench, and we can give it to these universities and try to get past. First, it'll help us catch up with where the global market is, but number two, we can try to actually start in a very small level commercializing at least one application.
Yeah. Yes, sir. Yeah. So thank you very much, sir, once again for your time and very nice talk. And please visit us as you do. Thank you so much. Thank
Sure,
you.
I'll see you in September, sir. Thank you, everybody. Namaste. Bye-bye.
Thank you, sir. Bye.